Good morning, everyone, and welcome to the seventh lecture of robot dynamics. Today, we're going to discuss floating-based dynamics. Before diving into the lecture part, let me quickly give you a couple of notes about some of the new corona measures that we have here at ETH. The midterm will be affected by that, so we will not be able to host you anymore in the rooms and do it the way we did it in the last midterm exam. Nonetheless, we would like to give you the opportunity to do the midterm, so we will handle it a similar way than last time, just that you're going to do it from home on your laptop. We will distribute files and everything through Piazza. There will be some measures put in place to make sure that you cannot work together. So do it for yourself, but we're going to send out detailed instruction in the days or week before the exam. But be prepared, same date, same time, same format, just not here at ETH. I hope this clarifies some of the questions that were raised on Piazza as well. With this, I would like to dive into some of the major questions that were asked and discussed on Piazza. First one was one more time related to what is the direction of the contact forces and when do we put a positive sign, negative sign, whatever. And I try to clarify this one more time here with an example of this single arm and also with the formulation of operational space, because I think here we see it very nicely. In case of operational space control, what we are having is on the right-hand side, we have this operational space force, which is essentially the force that is responsible for moving the system and at the same time, so producing the acceleration, at the same time also for producing the contact force. In other words, if this Fe is positive, then also the F contact force is positive. So if I have a force which is here in positive direction, this is produced by Fe, so also this one must have a positive sign. If you go back to the formulations we had originally, this Fc can be either on the right or on the left-hand side. If it's on the side of where the m times acceleration part is, then it is the force produced by the robot. And if it's on the other side, it is a force acting on our system. The second bigger question related to the contact Jacobian and to a rank discussion about the contact Jacobian. And I have several times here in the quizzes, but also in some of the larger scale exercises that you're doing, the questions for like what is the rank of these Jacobians and how can we intuitively figure out what the rank is. So what I'm typically doing is I'm asking myself in how many degrees of freedom these contact constraints that I'm imposing are locking in my system. Let's have a look at these examples here that we have with a biped and a quadruped. If I take a biped and I look at this contact point here of 1 foot, this contact point typically imposes 3 constraints. So we cannot move in X, we cannot move in Y, and we cannot move in Z. These 3 contact directions or these 3 constraints, they're completely independent linearly. So we have here a 3 times n Jacobian. And the rank of this thing here must be, sorry, of course, 3. The rank of this one must be 3. Now, if I have a second point here, this also gives a 3 by n Jacobian. Now, if I'm stacking these two Jacobians here, question is, are they linearly independent or not? And if I'm looking at these Jacobians are nothing else than I take the J is my dr after dq. Now the question is, what is in this R? Which parameters does it depend on? And as we can see, this constraint here must have these 3 joint angles in the parameterization of that position. That is the Jacobian part of the joint dependent aspects. So in other words, this one must be depending on these 3 joints, while this one must depend on these 3 joints, so they can't be linearly dependent. So if I'm looking at the total rank of this Jacobian and this Jacobian, the rank must be 6. So I'm constraining 6. I'm looking at 6 constraints that I'm imposing if I'm just looking at the rank of J. In difference to that, and let me draw this again in here. If you look at this point here of a humanoid in contact, this J here is again 3 times n. So we are adding 3 constraints. If I'm looking at this point now here, this point isolated is also a J element 3 times n. However, if I'm stacking these 2 Jacobians, I will not get 6 independent equations because they're all on one body, on this body, and hence there is a linear dependence on that. And the way I'm looking at this is, if I'm imposing this constraint that this point is not allowed to move and the other point is not allowed to move, how can I still move my foot? So I cannot move it in X direction, I cannot move it in Y, I cannot move it in Z, so all the positions are locked. I also cannot yaw it, so I cannot turn around this direction because I have 2 points on the ground fixed. I can also not roll. I can also not pitch, but I can roll. So along this one axis, along this axis here, I can roll around this axis. So there's 1 degree of freedom which is not locked. And that means we have a linearly dependent constraint. We have 6 dimensions in the J, but only 5 independent dimensions, which means that we have 1 internal direction, which is the distance between these 2 points. And we're going to see the exact same thing then also if you're analyzing the rank of this stuff for the quadrupedal system in the example that we have here. The third question that I would like to dive a little more into detail was this support null space projection and the interpretation of that, and also like how we get to this exactly. So what we derived last time was this slide here. So we came up in the end with a null space projector matrix, which I said is I can pre-multiply my dynamics equations of motion, and due to the fact that nc transpose times jc transposed equal to 0, this part here drops out. So I get dynamics equations of motion which are independent of my contact forces. So I get a direct relationship between torques and accelerations independent of the forces. So in other words, given my desired acceleration, I can directly calculate my torques. I don't have another constraint force that is somehow in there to be optimized for. So we're deducing an equation which depends on 3 parameters, namely on acceleration, contact forces, and torques, to an equation which only depends on 2 parameters. And the reason we can do that is because if you look at the dimensionality of these individual components, you see that depending on how many contacts we have, only a subdomain of the complete equations is kind of captured by the constraint forces, and the rest can be the free motion of the system. So let's analyze this a little more in detail. So what I put here on the right-hand side is the calculation of this null space. So we have here first the dynamics equations of motion here. And what we're doing is we're taking this contact force which comes in through the constraint, we're inserting this for our contact force here, so we get this second equation. Now what you're doing is we're exchanging this J dot Q dot with J Q double dot. So we have this equation here, which we reformulate. So we get this replacement here. And now we're doing a regrouping. So all what's happening is we're taking, here we have an MQ double dot. So we have identity times MQ double dot. And here we have a Q double dot. So what we do is we take this part here. So we take this part here, which gives that part. And then we write here a m-1 m in between. So we can take the m q double dot outside of the brackets and the m inside. So we have identity minus this term. Then we're grouping together everything which is related to B and G. So we have here identity part, and then we have here B and G. So it's again this component here which goes directly in here. And the same also on the right-hand side for the torque. And what you're ending up with is this NC transposed multiplication of the complete dynamics equations of motion. And if you have NC transposed, then NC is obviously just a transposed of it. If you transpose something, a multiplication of multiple matrices, we have to change the order of it. So what we're doing here is we're changing order. So m-1 goes first, and m is equal to m transposed. So we can write again m-1, and then here the whole term here essentially also stays there with an inversion of the transpose part. So that's how the whole thing comes together. Now let me discuss a little bit more the interpret this a little more in detail. If you look at a quadrupedal robot, then we have here dimensionality of 18. So we have 12 actuators and we have 6 base coordinates. So we have here an 18 times 18 matrix. Now, if this legged robot is in contact with the environment, and for an example here, what I'm taking, so if I have 3 legs in contact, that means I have 9 constraints. So my Jacobi is imposing like this FC is, FC is a 9 times 1 vector. I have 3 times 3 forces. And if I look at my Jacobi, I have the Jacobi is element R 9 times 18. So somehow I have 18 degrees of freedom, but I'm only constraining 9. In my actuator, I have 12 torques that I can produce. So I have 18 motions, 12 in torques, and 9 in forces. Now this Jacobian can maximally block like a 9-dimensional subspace. So that leaves me with another subspace where I can just control with the torques the motions. And this is what we'll see then later in more detail, but that's just the analysis of the dimensionality of these individual matrices that we have in here. So let me dive into some of the questions here, but before we do this, I will draw here one analogy. This equation that we have up here, we can also rewrite this in the following form. We can have M split in an M base and an M joint. The same for the B and G part. I sum this up in H. I have an H base and HG. Then for the joint, the same thing. And for S, so we have the selection matrix, which we said the selection matrix is doing nothing else than selecting the actuated joints. So this S times tau is nothing else than 6 zeros and then the joint vectors of the taus. So 12 actuators and 6 base which are unactuated. So I have here an upper line which is in red indicated where we have no torques acting, and we have a lower line where we have the torques acting. So in other words, what I can do here is if I take another projector matrix and I call this an N tau transposed, and I make this one equal to identity and then 0, in order to select only this red line here, the upper red line, then I get an equation which is from the dimensionality, it's only 6 dimensions, which selects this base part of the actuation, and it has no actuation torque in there. So we make it now linearly independent of torque. Essentially, the null space projector is now the null space projector related to the actuators. And similarly to what we're doing here for the actuators, you can also understand what is happening for the support part. So we're using dimensionality and just looking at that part, which is relevant for these two parameters. So the first question here is, by using this null space projection, we can ignore the contact forces. And this is true. So we are projecting it into a subspace where the dynamics equations of motion are not depending on the constraint anymore. So in other words, if you're looking back to when we discussed generalized coordinates and minimal coordinate, and we said like minimal coordinates are these coordinates that describe the motion which are consistent with the constraints. Then obviously in these minimal coordinates, we didn't have any constraint forces. So we reduced from a general set of coordinates to a minimal set of coordinates in order to get rid of the constraints. And then we had a description in that domain, which was constraint force independent. And this is essentially the same thing. We're doing a projection to make it independent of these contact forces. The second question is if there is a way to guess the structure of NC. So I interpret this question whether we can make certain decisions or certain statements about the dimensionality. How many degrees of freedom are we looking and how many are independent? And yes, we can do this. We will see this also in the following examples. NC is directly related to the JCs and to the stack of JCs of the contact Jacobians. And if these contact Jacobians are independent, that means they block this dimensionality. And the NC is essentially the remaining part, which is independent of that what is taken by this JC. So that gives the dimensionality or the rank of it. Now, if you write it in this manner as we have it here, with identity minus, again, a block matrix, then we will also always have this thing will always be in So we multiply the complete dynamics equations of motion with it. So it must be in R for a quadruped 18 times 18. So it's the number of base and joint coordinates times the number of base and joint coordinates. So it's an n by n matrix, but the rank of it is essentially full rank minus what is blocked away by certain aspects related to the joint contact. So we can see this primarily in this formulation here. So it's selecting this other substance. And then the question is whether we cannot cancel out NC on both sides of the equation. This NC could be canceled out if it was full rank, but it's not full rank. That's the point. So you cannot just multiply the inversion of it and then cancel it out. Otherwise, the whole exercise wouldn't make too much sense. Can I imagine this as a fixed system in the contact points? So maybe to answer these questions, I will go back to this illustration that we had here. So this humanoid, in principle, if we have one leg in ground contact, we could assume here 6 degrees of freedom that are locked. So we could have this as the base. That would mean if you step on your left foot is the base. If you step on the right foot, your right foot is the base. And you have all the time, you have to switch the set of coordinates to describe your system. And this is one of the shortcomings. The other thing is if you have both in ground contact, you have a closed loop kinematics. And that's not that easy to handle with minimal coordinates because the degrees of freedom that we have in this closed loop is obviously influenced by the constraints. With this formulation that we have here, we just have a very generic formulation that allows us to handle all these individual cases like in one single formulation. And what happens is just like whenever we switch contacts, our JC changes. There's a different contact which is active. So the stack of JCs changes, which means the NC changes, which means also that the dimensionality of the mobility in every contact pose can change. But again, like hopefully this is becoming a little more clear when we go through the exercise here. And then very briefly, 2 questions that are raised are related to the Jacobian and whether or not they are at the center of gravity. So here, make sure that you always have the center of gravity the same here. For the angular rate, it doesn't matter. So this is independent of where you are at the body. So here we have also the same point, but it doesn't really matter. It can also be another point. So the angular rate of a body is fixed, independent of its location. And there was one question related to the inverse dynamics control. And I want to just recap this for the sake of clarity here as well. If we write inverse dynamics, what we do have is on one side, how the system is actually moving. So mq double dot plus b plus g, which is the torque I'm providing to my system. And we are calculating this torque through a model knowledge, namely that we say this torque is equal to mq double dot plus b plus g, but this is now the desired q double dot that we want to achieve, and these HUTs are the estimated m's. And the desired acceleration q double dot, this is a function of an offset that I'm having in position, an offset I'm having in velocity. It can also be plus a q double dot star. So if I have a planner that plans also my q double dot star, then we can have here a feedback law in position, velocity, and acceleration that defines my actual q double dot. Now, assuming that we have the exact model of the system, so my m equals to m hat, my b equals to b hat, then we have these parts which cancel out, so b and b, g and g, and we can multiply with m inverse. So we multiply with m minus 1, which cancels out m and m hat. So we end up with that the acceleration of my system, my actual acceleration, is the planned acceleration, is a feedback law on the acceleration. And that is essentially this oscillator of a single mass, it's second order system mass with unit mass, and we define the stiffness and we define damping through Kp and Kd. And then the last one was related to static load compensation. This is something that I see very often happening also in the exam. Static load compensation is, I look at my tau, and I know my system is not moving, so I get this to 0 and this to 0, so all I'm ending up with my gravity part. And then people still add somehow the mass of the individual links to calculate this torque. But if you remember how this gravity part was assembled, namely only through Jacobi transpose times the gravitational force, then it's obviously clear that this torque is nothing else than the sum of all the external forces multiplied with the Jacobi at the point where they apply. And this is exactly this gravitational part. So we have here, if you would not look at the dynamics equations of motion at all the external forces are this m e times g, and their location where they apply are defined with the Jacobian at that point. With this, we go to the quiz that we had in this session. First one was related to contact constraints. We had this one card, and we asked for this card, which is the contact constraint with the point on the wheel, calculated Jacobian there, figure out the contact constraint, and then did a little bit of a discussion about the possible null space. So if I look at the contact constraint, so I analyze this for the point P. What I have to write is R of this point P, so the position vector as a function of my Q. And the generalized coordinate for this vehicle is, of course, x and the rotation of the wheel. We have an unactuated base, and we have an actuated wheel. Now, this point on the wheel is by x plus L sine phi in x direction, and we go by r plus r cosine phi in y direction. So this phi here starts in upper vertical position. That's why we have the r sine phi in x and the r cosine phi in y. Given this r, I can then directly calculate the Jacobian. This Jacobian is now we can either go through the velocity, or since it's a planar system and we only just in position, we do dr dq, and we get dr dx is 1, dr d phi is r cosine phi, and then we have the same part for the lower. Now what we have to do is set up this contact constraint. The contact constraint means that the point here, so if P is down here, then we must have 0 velocity. So here my r dot is equal to 0. So what I have to look at is the r for my phi equals to pi. So the point at phi equals to pi. That's that point which is at the bottom of the wheel, which is in ground contact. So I'm looking at my r dot at phi equals to pi, which is my Jacobian evaluated for the angle to be pi times q dot. So we take this matrix here, we evaluate it for phi equal to pi, and we get 1 minus r, 0, 0, 0, 0 as the Jacobian. Now that's the question, what is the third dimension? And that's a very good question. If I write it up here, I have it now just like for the most generic case for 3D. But of course, since we're in 2D, we can also just delete this last thing and have only X and Y that we're analyzing. I accept both in the exam. All I want you to be is consistent throughout your complete exercise that you do. Now, why do we use the Jacobian instead of the new Jacobian introduced with the floating base? So this is a floating base Jacobian. We have the floating base, which is described by X. That's why we have the complete Jacobian here. So we have also the XQ in our Jacobian in there. But we look at it at a simplified fashion. We are not looking at a car which can be somehow in 3D space with all the 3D orientations attached to it. We're only looking at this 1 degree of freedom where it can move, and we have one base coordinate in there. So it is a floating base, but only 1 degree of freedom. Now, what do we see in here? If I look at this first line, I have x dot equals to phi dot. So this thing here, this is nothing else than the rolling constraint. So if you look at this Jacobian, then we see actually the rolling constraint, something that we know by heart when looking at this example, but in fact, this is simply integrated in our Jacobian. Now, if I'm interested in the base motion, what I have to do is I have to look at the null space of this thing. So what I have to figure out is, what is my possible Q dot, which is my JC times, this is the R dot at the contact point. Obviously, this must be 0. So what remains is a null space projector times a Q dot 0, which allows me to change Q dot without violating this first contact constraint. So what I have to do is I have to figure out a null space. And now we have derived one possible null space with Jacobi transposed inversion, so the pseudo inversion of it, and then identity minus this part. This is a way we can do it, but this is not the way I would typically suggest you to do it. If I look at this matrix here, I can actually directly spot a potential null space projector. So let's look at the example. Let's look at, for simplicity, we only look at this block. We forget about the Z direction. And this must have rank 1. So we have one row which has zeros and zeros, so this can't be full rank. That means there must be at least one dimension in null space. And since rank is 1, the dimensionality of the null space must be also 1. So can I find a matrix that if I multiply this matrix with the Jacobi transposed, I get a 0 with it? So to cancel out the contact force. And one possible solution is what I write up here. If I multiply R1 with 1 minus R, this just cancels out, so I get a 0. This is one possible null space projector. And if I do another analysis, all I will get is something which must be on the same line. And since it's only one line, there's only one direction that can span it, so it will be the same solution no matter what. If I would have a plane that is spanned with this null space projector, I could have the same plane expressed by different vectors, but they're all expressing the same plane. If I'm talking about one direction, then this is purely defined already. So this is the null space projector. And what I'm seeing in here now is, in essence, how my base should move and how my joints should move such that the thing is consistent with the contact constraint. So if I'm varying here, if I give a random number here in alpha, then I know that I have to move my x in r times alpha, and I have to move my angle in alpha. So this is nothing else than, again, a motion which is compliant with the contact constraint. Now here, of course, it's trivial because it's only a two-dimensional system with one constraint which leaves one direction. So we can immediately spot this from the rolling constraint. We immediately spot in how these joint angles are related to each other such that the constraint is valid and we can move. It's a little more tricky for a legged system or like a complex robot arm, which has a contact constraint that imposes constraints on all the other joints. And then you have a certain way of how all the other joints can move without violating. We then looked at more complex systems, and particularly here the quadruped, and I ask you to identify the total constraints that we have here, the base constraints, internal constraints, and the uncontrollable degrees of freedom. So we go through this together here. So we have the first example where this legged system is in air. So there is no JC, no point is in contact with the environment. So JC is here, there's no JC, so the rank here must be 0. So that means also if I have my JC, just as a reminder, this was my JC base and my JC joint, stacked vector here. So if I have a JC which is 0, then obviously also the base part is 0. So that means if I take rank JC minus rank JCB, this is also 0. And if I look at the 6 minus this rank is 6. So in other words, we have now 6 uncontrollable degrees of freedom. So these constraints do not describe how the base should move. And in fact, I can take this robot, I can move it in 3D space as I want without violating any constraint and independent of what the joints are doing. Then we look at this second scenario where we have one point in ground contact, which means one point imposes 3 constraints. Then we have the base part. So these are 3 independent degrees of freedom. So that means also the base part must be 3. And if I look at this internal degrees of freedom, this is obviously 0. 3 minus 3 equals to 0. And if I look at the uncontrollable degrees of freedom, I have 6 minus 3 equals to 3. So in other words, I have, if I lock here my joints and I put my quadruped on the ground on one point, I have 3 degrees of freedom that I can still move that without violating the constraint. And these 3 degrees of freedom are essentially the rotations around that point of contact. I can move my base around that point of contact, but I cannot move it arbitrarily in position directions and motion directions. So I have 3 constraints that act on my base. Then the third element is rank of JC. And this is related to what the statement I made before. So we have here these 3 joints, and we have in the back these 3 joints. So obviously these 2 constraints, each 3-dimensional, they must be linearly independent because we have 3 different coordinates that are in these Jacobian. So we have here a rank which is 6. Now what is tricky is to understand what is the rank of my base on my base. And again, like I would apply here human intuition. If I take this quadruped and I lock all the joints and I put it on the ground, I essentially get the base on this line between the 2 points of contact. So it cannot move in XYZ. It cannot make a pitch around this line or yaw around this line, but it can roll around this line. And this is exactly this 1 degree of freedom that remains free for the base. So the base can only move in one in a one directional manifold. So we have here base constraints are 5, which means there is one internal constraint. And this internal constraint can be interpreted that we have a force between these 2 points. So I can change the torques in my joints to modify the base motion and everything. But I have one dimension which I can change my torque that just changes this internal force between the 2 contact points. It doesn't change anything in the motion. And that's this internal direction that we see here. Then if you look at the uncontrollable degrees of freedom, it's also 1, 6, minus 5 is 1. So this is this one direction. Then let's put 3 legs in ground contact. Here we have 9 total constraints. If I have 3 feet in ground contact, obviously I cannot move my base anymore. So the base rank must be 6, and I have no uncontrollable degrees of freedom. If I look at the difference here, I have 9 minus 6 equal to 3. So I have 3 internal directions. And this is also indicated here with the red arrows. I can produce internal forces among these contact points, which allow me to redistribute the ground reaction force without changing the way we're moving. And this is actually what we're doing permanently. If we're sitting somehow, we are changing our muscle activity without changing the way we're sitting. We can sit very relaxed, or we can like stiffen up things and not produce any force at the back of my seat or at the contact points with the environment. So we have the same pose, but you have different interaction with the environment. And that's exactly these null spaces that we see here. And then the last one, same. So here we have 12, 4 times 3. Then we have again 6, 6, and 0. And here we have 6 degrees of freedom, internal directions of reaction forces. All right. With this, we jump again back to this card pole pendulum and do the last exercise I asked you here to do, which is determine the null space and interpret the capability to move and apply forces by the actuator. So we did the same analysis already when we looked at the kinematics only, and now we do it with the full dynamics. 3 cases, both active, only vertical or only horizontal. So the first case, when both are active, what does that mean? That means that we have this JC, so everything is there. And if you look at the rank of this JC, this obviously has rank 2, which means that the null space is 0. There is no null space. And if I take here a null space and I multiply this and C here on this equation, that means literally the system cannot move. So there's no subdimensionality left that allow me my system to move. So in other words, these constraints fully block the system. However, I have a torque here on that thing, which changes the force to the environment, but it doesn't change the way we're moving. So these constraints fully defines the motion. We can have an actuator, but this actuator just changes the reaction forces to the environment, doesn't change the motion. Then second case was vertical motion is locked. So what we're looking at is really only this contact constraint, the second one. If you analyze this is a 1/2. Rank is only 1 here, which means we can define a null space projector matrix, which is 1, 0. So if I multiply JC with NC, I get a 0, and that's the definition for this null space. Is one possible null space projector. So I can now multiply this upper matrix with this NC. So what I'm doing in essence from this upper matrix, I'm selecting this upper part of the equation of motion, right? So I have here a 1, so I'm selecting this part of the equation of motion. let me indicate here. So I have this part of the equation of motion, which cannot be changed by torque. So whatever I'm applying as a torque, it doesn't change my motion. However, the torque itself can be used in order to modify the force, because there is an NC transpose multiplied by S transpose. This has a null space, which is again one-dimensional. So if I'm inverting this here, I get a torque and I get a null space torque, which changes the force. And this is also here intuitively clear. If the motion is locked in vertical direction, I can move my cart here in X direction. And independent what torque I'm applying, I can just move this freely. Everything is friction free. If I change my torque here, all I'm changing is my reaction force. And similar to that, we can also analyze then if the horizontal motion is locked. So now we have the case where we have this moving in horizontal and in vertical direction. What we have here is now the second line is 0. Again, rank is 1. So rank of JC here is 1. This means I have a null space. If I have one possible null space is, again, I can look at this JC vector and I find a multiplication that NC times JC is equal to 0. And I can look also at NC transpose times ST, and this is now a -1. So my torque here really has an influence on the equation of motion, on this one-dimensional equations of motion. So I'm left with a one-dimensional equation of motion, and my torque has an influence on that. So with my torque, I'm directly shaping the way how my cart is moving. So if I have my NC transposed pre-multiplied here, I'm reducing a two-dimensional equation of motion to a one-dimensional equation of motion, which is independent of the contact force. And that means we have a one-to-one relationship between torque and motion, and the force is just an effect of how the system is moving and how it's actuated, but it cannot independently control the reaction force. So with this, we are done here. Thank you all for joining. I tried to answer here a couple more questions. And but for the rest, if you want to leave, I think this was the most important part. So let me start with the second last. Why can't the base move in Z direction in the last two cases? So if I make a cart here and I'm only defining my X coordinate, what I mean is that we have here also wheels on top. So it's kind of blocked between an upper and a lower wall. If this would not be the case, I would have to introduce additional degrees of freedom. So I would have to introduce here also a Y and a phi coordinate for the base. Then the system would be more generic, more complex, and then we could lift off. And everything would be depending on the complementary constraint that the contact forces can only be positive and not negative. How should we choose the NC, generically or intuitively? I personally would always look at these questions from an intuitive perspective. We try to ask questions which can be solved without a lot of computational means. If things are getting more complex, and that's also why we're doing these exercise sessions in a very generic way, then take your tools that you have in your toolboxes to calculate the null space directly with the functions that are there, which are numerically stable, where you don't have to go through like complex analytical derivations and stuff like that. So if you have other tools at hand, do it generically. If we do an exercise by hand, try to do it intuitively. If you can't do it intuitively, at least write down the equations on what you would evaluate if you would have tools at hand. So if we use the new Jacobian for floating-based systems, it seems that we have to put in 3D even if you have a planar system. This is not the case. I mean, a floating base in 2D means we have X and Y and one angle. That's the floating base. And then the actuated joints here are one link joint, this tau A around the phi axis. And that's the same for humanoids, arms, or quadrupeds, or whatever. So in 2D, floating base description is with two positions and one angle. So the question is, so there are several questions related to when can we now take the Jacobian as partial derivative and when not. So what I'm doing here on the slides is I'm typically very sloppy, so I always write this a partial derivative. If you have your toolbox, what you're doing at the beginning is you have something that derives all your Jacobians and everything for every point you're interested in based on the right infrastructure that you have at the back end. You can still do partial derivatives, and you can also do partial derivatives if you're in 3D space under certain constraints. In particular, if you're looking at positions and cues, then it's still okay to do it. Just make sure that you know what you're doing. We are trying to always ask questions here, which you should be able to do by hand. And as I said, if you are going to like more complex systems, then this is like something you ask your toolbox for. So give me the Jacobian at that point, or give me the rotational Jacobian at that point. We have seen how we derive this. So we have the whole pipeline to derive this. It's all just an evaluation of a subsequence of a couple of rotation matrices and offsets that we have to multiply with each other. So I know that you know how to do this, and that's somewhere stored in your pipeline, your tool chain, and then you just draw the Jacobians that you need for certain elements. And last question here again is, do we need to restrict the acceleration of the contact point? Whenever we are talking about dynamics, we're talking about acceleration. So any constraint, any formulation of a task, of an objective, how we would like to move or whatever, has to be somehow propagated to acceleration level. If I have a constraint on velocity, if I have a constraint on position, I have to propagate this to constraint on acceleration level. In an ideal case, when initial conditions, everything is valid, you can just look at the acceleration. If you would have to numerically stabilize these things, you would have to have feedback gains also on velocities and on positions. But we are not looking at this in here. And the last question was like whether there is another midterm. Yes, there is another midterm as introduced in the first slide. All right. So I hope this answers all the questions that were raised in here. Okay, so one last question. Could you repeat why for a vertical locked motion, the first row has to be canceled? So vertical, what did we look at? So we had R at the contact point. The velocity was x dot at the contact point and y dot at the contact point. and this was equal to 0 and 0. Now, if you look at only the vertical part of it, then obviously only y dot must be 0. We don't care about x dot, we can freely move. If you're looking at the other example where the horizontal motion is blocked and the vertical is free, then only this line has to be staying in the constraint. So I have only a one-dimensional constraint, which means I'm only looking at one row on the Jacobian. The Jacobian is nothing else than a stack of all the constraints. If you're stacking multiple Jacobians of multiple contact points, is as if you would stack a Jacobian for X, a Jacobian for Y, and a Jacobian for C. It's all just a linear dependence between Q and the constraints. All right. So with this, thank you all. I think that clarifies hopefully everything, and see you next week. I will upload again the videos for next week's session tonight, and same for the lecture notes. Thank you all, and see you in a week. Bye-bye.